So welcome back, and thank you for coming, for cutting short the coffee break. As I said, we had a very nice session, and we broke the protocol and the schedule, but it was worth it. That's a karaoke spirit. So that's what happened, but it was very nice. Now we have the next highlight is from the Nobel Laureate Jean-Marie Lehn. He will be speaking about steps toward complex matter chemistry. He's doing it on Zoom from Paris, France. Please.
Oh, from Strasbourg, not from Paris.
Oh, you're in Strasbourg. Yes,
Yeah.
I remember.
In the east of France.
Please, the Zoom stage is yours.
Okay. All right. And that is the Lipkovsky Symposium, correct?
Well, it is part of Lipkovsky Symposium, but you are a plenary lecture where all participants are present.
All right. Okay.
They are from all fields of science and in many other fields, law, medicine. So you have a diverse, multidisciplinary audience.
Yes.
Plus
the
participants of Lipkovsky International Symposium. And Professor Lipkovsky is here. I saw him.
Good.
He's there. He's present.
Good. Hello, Janusz. Very nice to be back here at this meeting. I suppose you are in the audience. And
yeah, he's here. He's here.
He's here. Okay, very good.
Yeah.
Hello. And I will start my lecture. I did not know that it was so different audience, but I think for the chemistry lecture, the audience will be already self-selected. So, okay, I want to give a few ideas about steps towards complex matter. It's of course a very big story, but I will shorten it, and if it's a bit too long, I will drop a few of the slides. I've handled these kind of things a long time ago. So, complex matter, where do we get there? I start with very early on. After the Big Bang, there was a big period of what is called inflation. That means that the universe very, very quickly increased in size enormously. This was no chemistry. There was only physics and the starting of the laws of physics. So at that time of physics, then when the universe cooled down, progressively went to the period of chemistry, when atoms formed, when the atoms could get together to make molecules. So chemistry started around here in our universe, in the development of our universe, the age of chemistry. Luckily, it didn't stop there. Chemical entities became more and more complex. They formed containers and sort of aggregations, and out of that, property appeared, which was life on our planet Earth around that time, the age of biology. Again, it didn't stop there. And the living organisms, which had appeared by a process we don't understand yet, but we will certainly understand because we exist. And so we'll find out how this worked at some stage. So it continued to evolve, and a new feature appeared, which is even more important than life in some respects, but it's a sequence, and this is thought. That is why we are here today, is thinking, and this is, of course, steps towards more and more complex forms of matter. Okay, this then represents a stepwise evolution of the universe from the laws of physics to thinking, which makes us understand the rest. Now, science is the activity, human activity, which makes possible for us to try to understand what's around us, what has been going on. And I must say that it's quite impressive that a living entity sitting on a piece of dust in a huge, huge, huge universe is able to understand, or at least to try to build up the knowledge for understanding the evolution of our universe and how we came about. The big question then is, how does matter become complex? What are the mechanisms by which matter can become complex? From the elementary particle to the thinking organism, and maybe the higher forms of complex matter, which we don't know about right now. For giving an answer to that question, mankind developed science, which is based on a number of areas of investigation. Let me just cite three, which are, I feel, the ones which are the basic ones. Physics deals with the laws of the universe. This is answering the question, why is it like that? Physics is the basic laws, and everything is controlled by these laws. Biology deals with the rules of life. These are rules, not laws. The laws are given by physics. So how does biology function? And chemistry has a very important mission, which is to try to understand how to bridge from the why to the how, from the general laws of our universe, which control everything in our universe, to specific expressions of these laws, like life on our planet, and very probably on other planets, on many other planets, probably. So the answer to the question is a very simple word, self-organization. It means that our structure, the structure of our universe, is such that it will self-organize. It will form organization. And one would even say, this is a bit going far, but I am convinced of it, a cosmic imperative, meaning that our universe is structured in such a way that life is not an accident. Life is a consequence of the laws of our universe. So, chemists have built up the art and science of making molecules from atoms, taking bricks and building up houses. This is molecular chemistry. And these bricks are linked by strong bonds, called by chemists covalent bonds. Beyond that, then, comes the fact that molecules, when they get together, they can interact. And this leads to a chemistry which lies beyond the simple isolated molecule, and we call it supramolecular chemistry, which deals with the interactions between chemical species, not their own constitution, which is, let's say, molecular chemistry, but the way things happen when they get together. And three main properties were studied along the years. How do molecules recognize each other, one another? How do they react with one another? How can they carry one another through barriers like a membrane, for instance? Let's look at the most basic feature, molecular recognition. Here I show a cancer cell and two killer cells. The killer cells have the mission to destroy the cancer cell. How do the killer cells know that the other one, the other fellow, their partner, which they are just attaching to, is a cancer cell? Because something happens between the bodies characterized by this cancer cell and the two killer cells, defined by a membrane. And these membranes are full of molecules, of course. And as they get into contact, then one tells, so to say, they have a sort of a transmission of the information of what the entities are. That one is a cancer cell and the other one are killer cells. This kind of interaction, which is molecular recognition, is the basis and the most important feature in living organisms. All molecules must recognize, otherwise you can't exist. And this molecular recognition requires binding interactions between the molecules to become supramolecular, so to say, and information for selecting. The information is contained in the structure of these molecules, the way they are built, the shape, and so on. Now, there was very early on a very nice picture, strong picture given by a very famous chemist in the between the 19th and 20th century, and this is Emil Fischer. And Emil Fischer published a paper, a very famous paper in 1894, where he said that to act on each other, molecules have to fit together like Schloss und Schlüssel, like a lock and a key. This was published in a paper in 1894, a very famous paper, which is the basis of recognition between large biological molecules. Incidentally, he got his doctorate in Strasbourg in 1874 in the laboratory of Adolphe von Baeyer. Now, of course, this being said, that in fact, supramolecular chemistry deals with all the properties resulting from the aggregation between molecules. And there are many applications in life sciences, which is probably a very important contribution and one thing one should look at. First of all, it's quite clear that drug discovery deals with molecular recognition. It is based on the recognition between a synthetic molecule you may call a drug and a biological target. And this is a process by which one can try to influence functioning of an organism through the introduction of a key, the synthetic molecule, binding to a specific biological lock. And of course, this binding has to be as specific as possible so as to minimize side effects. And I will just show you a few examples of what we had been doing, just as a picture, as a way to give some examples of what has been done along the way. First of all, as I said, drug discovery rests on molecular recognition. We also developed a diagnostic tool using immunofluorescence, where you see here a unit which contains a europamine, which can fluorescence with a red color, and this can be attached to immunoproteins and leading then to the immunoanalysis system, which is shown on the right, thanks to the hard work of Dr. Gérard Matisse at a company called SysBio. So that was something quite interesting, an application which resulted from some of the initial work. Another property is if molecules can bind a piece of DNA, a gene, it can help that gene to go through the cell membrane, go to the nucleus, then become RNA, and then be translated into a protein. And this process is used for gene transfer, which can be used either for gene therapy or for biotechnology. And this is a very important process. Gene therapy is, of course, for instance, for diseases like cystic fibrosis, for which a lot of work has been done. And biotechnology, this is for the use of this gene transfer process for making genetically modified organisms. I know that there's a bit, for many people, that's a problematic type of development. I think making genetically modified organisms is a must. We must use it, and I'm sure that we will use it, despite opposition from a number of people who don't know what they're saying. So supramolecular materials can be developed, like supramolecular polymers. That means polymers which result from the binding together of monomers through weak non-covalent, through weak attachment, weak bonds. And this was then developed since the first paper we published there was in 1990. But many years later, a development of quite some interest appeared, which I will just show you here. In 1990, we introduced the notion of supramolecular polymers. Then the work developed in many laboratories, and also biocompatible polymers of that type were made. And the colleague in Eindhoven, the group of Bert Meyer, they developed different types of supramolecular polymers, and it resulted in a worldwide application in 2013 for cardiovascular implants. A small Dutch company, Celtis, made supramolecular polymers for the treatment by surgery of children with severe congenital cardiac malformation and who needed cardiac reconstruction. And this was done in 2013, notice 23 years after the introduction of the concept of supramolecular polymers. And I show you now the first little girl who was operated on. This is Dominica. he 3 months after implantation of some of these polymers into her heart for correction of the heart. In fact, it was a separation between the ventricles, which was done, and it was done by Professor Leo Bokeria in the Berkulev Center for Cardiovascular Surgery in Moscow in 2013. And she's fine, as you can see. This was for 3 months after implantation, and now many more children have been implanted, many more than 10. The company developed also heart valves, which are of course more difficult to make because they have to move. And now they are working, as far as I know, on tubings for dialysis also. So I think it's developing quite well. And I was told by people of the art that it's a breakthrough in surgical practice. It made us extremely happy, of course, to see that a concept developed earlier just for knowledge, which is, as it is usual in science, then comes to an application because many people work on it, are interested in it, and ultimately something very useful like this unpredicted type of application, which you see here. Another possible application of this type of materials is that they can be self-healing polymer films. And I show you just the result of that self-healing because of time, I will be quick. Here is a transparent film, very nice transparent film. It's completely transparent. It does not deform the writing here. And so it is very homogeneous, and one can then cut it with scissors, superimpose the two ends and press where it is superimposed, press very simply with the finger. Of course, can also be done in a much more advanced technology, advanced fashion than just using the finger. You can then press and you can stretch and it sticks. So this is a self-healing film, which can be applied to many other cases. Some developments have been made around the world, but I can't tell you about anything. This is something we have done at that time. Now, one important step towards more complex matter is then to look at this self-organization feature, the fact that entities can spontaneously organize and lead to an organized structure from given building blocks. Of course, everything depends on these building blocks, which have to be correctly designed so as to form the architecture. A best example is the formation of a virus. A virus is a dead entity. It is made of biomolecules, but it is not living. And the tobacco mosaic virus was rather well studied, very well, in fact, by our group at the start. And you see here that this virus is 2,130 protein subunits, has this as building blocks, one molecule of the genome, the RNA, and represented on the left is that the molecules can be the molecules which form the supramolecular assembly, represented as a piece of pie, which then has a sort of a conical form, which then can assemble, and because of the shape and the types of interaction between the pieces, it spontaneously forms a disc, then a loop washer, and then it ends up in a helix. And the helix then, in the center of the helix is contained the RNA of the genome of this virus. On the right-hand side, you see more detailed representation, and down here even more detailed, showing that there is the shape of the building blocks of the bricks is such that when they get together in a given orientation and they are maintained in that orientation by interaction between the face-to-face, and so they recognize that there's a surface-to-surface recognition, which then allows for the formation of a disk and then for the other development. This type of process, of course, looks like magic, but it's not magic at all. It's just the law of chemistry. It is interactions. It is structural chemistry, it's organic chemistry, it is biochemistry, but it's no mystery, no magic. And this can be called a programmed chemical system, where then you can think of making non-biological objects as building blocks and seeing how they can get together to generate given architectures. I will show you now a few examples of those, which we have done, but there have been many laboratories are working on this area then. Here we use as bricks organic molecules which can bind metal ions, ligand molecules. These are the bricks. The connections between these bricks is brought by the binding in a sort of a cementing fashion by the metal cations. So if you choose well the units which bind the metal ions and the geometry of coordination of these metal ions, then you can generate spontaneously, but under the control of molecular assembly rules, which depend on the structure of the brick, of the binding sites, as well as of the coordination geometry of the metal ions. You can make a number of different architectures. Very great variety of such architectures have been developed around the world. And I show you some we have developed initially. In fact, this was one of the first ones. Helicates, a double helix and a triple helix, totally artificial, nothing to do with DNA, nothing to do with organic or biomolecules. This is a double helix with two molecular strands, one artificially, of course, computer colored in brown, and the other one in blue. These are maintained together by copper ions. You don't see them here because they're a bit hidden. And on the right-hand side, a triple helix with three strands, a blue, a white, and a red one. And here you see the middle ions, the yellow dots here. These are nickel ions in this case. It works, however, also with iron and with cobalt and with zinc and so on. Another type of structure is the one shown here, where 6 molecules, 3 horizontal and 3 vertical, the blue ones horizontal, the red ones vertical, held together by 3 times 3, that means by 9 silver ions, which form a very nice grid. And this is self-organized, as you can see. It leads automatically when you mix together these silver ions. It works also with copper 1, but just to give you an example, you mix together silver ions, the correct molecule, which is this molecule. You don't see it in detail, but it has all the binding sites needed for connecting with the metal ions, with the silver ions, and you get this grid. Another one is this circular architecture, where now 5 different molecules are maintained together by iron, 5, white, red, blue, yellow, green, and blue. And they are, you see here, the metal ions, which is iron in this case. And in the center, there's a chloride ion, but I can't go into that. That was a very important molecule for us, but I haven't time to get into it. Finally, I would like to show a unit which has 2 different types of bricks. The ones I have shown up to now has the same molecule and number several times. It's a sort of aggregation built up from the same bricks. In this last case, there are flat molecules in blue, there are linear molecules in red, and they are linked together by copper 1 ions. That means that there are 4 flat ones, 3 linear ones, and there are also then 12 copper ions. That means altogether 19 components building up spontaneously from their elements into a nano cylinder, as you see on the right. And this have nothing to do, just to design correctly the pieces. Now, this type of spontaneous formation of a complex architecture with specific properties, which will depend also on the metal ions, is of principal interest, in principle, for self-organization of nanoscience and nanotechnology type of applications. I can imagine that at some stage it will be possible to not to have to construct nano functional devices, but they will construct themselves on the basis of how the bricks and the cementing units are built. So one can hope that at some stage, when we go from the component to the device directly, and one would not need then to make the object, to fabricate, but it would make itself to self-fabricate. Of course, that would be the ultimate fabrication. I'm quite convinced that this will happen, but not for the moment, not yet. Although some of the entities developed in a number of groups have optical properties which are of interest, or electrical properties, and so on. Now, one feature of supramolecular chemistry, which was not at the beginning really taken much into account, although it existed all the time, is the nature, is the essence of supramolecular connection, supramolecular architectures. It is that the binding, the interactions between the building blocks of the final architecture is rather labile. So you can call it a dynamic chemistry. It's a chemistry where the objects of that nature, of the supramolecular nature, can fall apart into their pieces and reconstruct, reassociate, but in the process, there may also be some changes due to changes in conditions, for instance. So this is a dynamic, non-covalent chemistry. Then one can think of making molecules themselves dynamic. This can be done by importing reversible covalent bonds, bonds which form and break reversibly, into molecular chemistry. If one does that, this reversible bond, that makes then molecular entities also dynamic, and that's a dynamic covalent chemistry. If one wants to put this feature of being reversible, of being dynamic under one heading, one can say it's a dynamic chemistry which lies in the constitution of the object. It's not a question of kinetics. It's not a question of reactivity. It's a question of constitution, where the constitution of the chemical object can fall apart, can dissociate, reassociate. And if during this process the conditions change, like for instance, addition of a compound, change in temperature, or different things, physical stimuli or chemical effectors, then one results in adaptation. In other words, the object can change itself. Variation in the constitution can occur by exchange, incorporation, or decorporation of components as a response to either a physical stimulus, which can be, as I said, temperature or pressure or electric field, or a chemical effector, which could be protons, can be cations, anions, molecules of different types. So this leads down to a chemistry which you can call adaptive, because the chemical objects adapts to the circumstances, adapts to what is happening around it, to addition or removal of different components from this mixture. So when it goes, therefore, towards one more step in complex matter, which is initially, of course, is very important to be able to design by introducing molecular information, with well-designed information and programmation, which then leads to the controlled generation of the molecular or supramolecular entities with given functional features. The next step is then to try to make systems beyond the design, a system which by itself will select what it needs to build itself up. And this needs dynamics and diversity. Diversity because if you want to make a choice, of course, you have to have diversity so that the process can choose the object needed to generate the final structure, and dynamics, meaning that you don't want the first collision between the objects to be too strong, but it has to be able to adjust, to dissociate, to adapt to the change in circumstances, the change of the medium, for instance. And this then leads to the process of adaptation in response to physical or chemical agents. And this is a very important process, and it leads to adaptive chemistry, which is now a major field for us in our own work. Again, here, of course, they haven't time to get into all that, but one can see a number of applications, applications which have been tested. I don't want to get into it, is to make biologically active substances in a way that the key builds up spontaneously to bind to the lock. The lock selects the pieces which gives the best key, if I may use the language of Emil Fischer. So that lock builds up its own key, which means for biological molecules, for instance, a biomolecule builds up the substance which best binds to it. And one can also make materials in that way, but again, in this short time, I haven't time to get into it. Now, let me just show you one case where one gets just an illustration of optical changes induced in these dynamic polymers by bond recombination. If we have two films of polymeric films formed by two components AB and A prime, B prime. A and A prime are the same category, B and B prime the same category, but different types of molecules. Now, if the connections between the two, the A's and the B's are reversible, then when there's a corner where they overlap, what do you expect? You expect that the two new combinations which were not present at the beginning will, in principle, will form A, B prime and B, A prime with B. And if there is a color in one of these two new combinations, you will see it. Or if there's a fluorescence, you will see it. So I had Japanese co-workers then, they liked these little pictures. Here is a cat. The head and the ears of the cat is AB. The inside of the ears, the eyes and the whiskers, the mustache, is A prime, B prime. And they are here built together in this nice picture. Now they're superimposed, and also only the superimposed parts will there should something happen. Indeed, as the reaction goes, you heat up a bit to make it quicker, you get yellow colors where it's superimposed or fluorescence where it's superimposed. This shows that indeed these dynamic features do play that role, and it proves that it works, that you get indeed the interface exchange and the reconnection of the A's and the AB and the A prime B primes. A very interesting experiment was done, and this is going towards the end now. And but I would like to say a few words about this one. Maybe I drop one slide later on. Adaptation to surface adsorption. If you take this molecule, this was done with one of my colleagues, Professor Paolo Samoi, who is working on nanostructures and nanochemistry. So if you deposit this molecule with this aldehyde group, if you dissolve this in phenyloctane and add 3 different diamines, you would expect that this aldehyde will react with the NH2 groups and generate a whole lot of different types of entities. And that is what happens if you're in solution. If you are in solution, then you get a statistical mixture of connections between aldehydes and amines, and in the conditions in which we operated, it was in such a way that we have a mixture of the monoamines of the 3 different diamines, B2, B6, B12, and the other NH2 is free. There's only 1 to 5% of BCMA. So this is just a mixture which you get in this condensation reaction. Not very interesting. In fact, rather useless. But then you take a drop of this solution and put it on the surface of graphite and then look at it by scanning tunneling microscopy. What do you see on the surface? What you see on the surface is a very organized entity, which is the bis imine of the C12 compound. That means of this compound, bottom left, where both amines have now become imines, leading to this molecule here. which deposits and makes these very nice arrangements. What does that mean? Something very important, that the simple adsorption of this system on a surface drives the reaction to completion, making piece images, and drives the selection of the components only the C12. In other words, it's quite startling, and sort of looks even like magic, but it is extremely simple. It's just that in this mixture, in this potential mixture of all kinds of combinations, the adsorption on the surface, the thermodynamics of that absorption, drives the reaction and drives the selection. So it's an adaptation to the adsorption on the surface, very powerful in terms of chemistry occurring. It's a self-organization which drives the selection, and one can even say in some ways that it has something to do in the origin of complex matter, can be living matter. What I mean by that, not that these molecules have something to do with the origin of life, just that the simple adsorption forces on a rock, it can be granite, or it can be some sandstone, it can be different types of surfaces. The adsorption will operate a selection process, and it will give rise to drive a reaction and will also be able to select. So it's very powerful as a very simple physico-chemical process, has a very strong chemical influence. Now, I haven't much time left, so I will drop this slide, but I would like just to make you understand a very important process. I will say it in words, I will show a slide, but just to show you the concept. So I drop this. This is a network which I could discuss in more detail, a network of 4 constituents, which is square, and I don't want to go more into that, although there's something very important, but I haven't time for that. So let me just show you now something which I think is quite important. First of all, if you are in a solution and have 4 components, 4 these entities, constituents, red one, the blue, the purple one, the blue one, and the green one. These are made by combination of objects down here. You see this here is one of the objects, there's a green one, there's a red one, and so on. So they form and dissociate and form and dissociate and so on. And this is in solution. Now, if one of these constituents here has a property like forming an organized entity at a different temperature, when you reach that temperature, then the system generates the object which forms the organized structure. In other words, if you start with a solution of these 4 objects, and if one of them, for instance, the green one, I choose the green one, at some temperature leads to the formation of a more organized structure, which means a gel, then if you go from a solution, which is of course not very organized, it's a solution, to a gel where some interactions exist, a jelly, there's interaction between the entities, then something very interesting happens. When you cool down, you go from the dissolved entity to the organized one, which you can measure by NMR and so on, and then you get a very strong amplification of that assembly which forms a gel. In other words, it's a sort of a catalysis of the formation of the unit which breaks the gel simply because you get into the temperature range where the gel can form. It's a self-organization driven amplification of those constituent, of that constituent in this case, that reinforces the organization. Organization in this case leads to the reaction and the selection. So what does that mean? The order increases, or the organization increases from left to right, and the increase in order, the potential increase in order drives the system to organize. It's a sort of, as I said, catalysis of organization. When you read it, of course, you destroy it, so you can go back and forth. And the conclusions of that are that if you start with a statistical distribution here, as you can see, the statistical distribution of 25% of each of these objects, as you go to the gel, the green one is the one which forms the gel, so that one is strongly amplified. As a consequence, the one which does not use the other components, that means if this is AB, this will be A prime, B prime, is also amplified. This I call agonist amplification, but I haven't time to go further into that. It's published, and there's a paper about 2 years ago. And so I think it's a very important process also, the fact that if order forms, if something leads to organization, there's something else which results from the fact that two entities have led to the organization, the other one is left apart. It's agonist amplification. It's also amplified. Now, let's translate that into words in a way which is sort of, just stressing what is the main property. If in a thermodynamic system where there is an entity, I will make it simple here, where there are 4 entities and one of them can lead to order. If you reach the physical state, in this case temperature, where that organized object can exist, the system will rearrange so as to generate that entity which leads to the organization. In other words, as I said, if organization can happen, it will happen because the system generates the object which can organize and which does organize. That's a sort of a drive to organization. And I would even say that it's imperative and an intrinsic property of visible matter. It is a way to go from given mixtures of, let's say, undefined or of different types of objects to a selection of the one which leads to organization. Okay, one can discuss problems that if the system becomes too complicated, one has to introduce containers and so on, and that would be the next step because it opens the path of leading to primitive cells and maybe a process which then in the organization of non-living to living matter will be a very important one. So I think that is more or less what I want to tell you. I have another slide, but I think you're okay. Let me just quickly go through. Molecular chemistry is then followed by supramolecular chemistry in terms of complexity. Then it gets organized, dynamic, adaptive, and then it makes networks because all these objects which can exchange pieces, they talk to each other because if one exchanges a piece, the other one will know, so to say, about this exchange, and the system will then sort of, the pieces in the system talk to each other, and that is more and more complex states of matter. So that's what I wanted to tell you. I hope that the special cases are not so important, but the concepts which are behind these special kind of illustrations are the things. What is important is the conceptual part of it and the way in which it expresses itself into complex matter. Thank you very much for your attention.
Thank you, Professor Lehn. We appreciate it. You hear me?
Yeah, I hear you very well.
Yes. So inorganic and organic chemistry together in supramolecular science, correct?
Yeah, so to say, yeah, this was something people often have asked me. Of course, inorganic coordination chemistry existed before there was, let's say, before we defined the field of supramolecular chemistry. But supramolecular entities always existed also. And let me just give you this, maybe make things clear. Just give an example if I have the time, yeah?
So that's SIPS. We combined all field of science under one roof.
That is what we should do. Yes, it's not always easy.
Yes, that's what they've done it since 2003. That's what we're trying. Under one roof, all field of science, and your lecture is exactly about this. So there is no definition, application in biology, in humans, and in organic chemistry, correct?
Yeah, I see it was a bit covering a lot of ground, but let me just give an idea about what one can see as a difference between the step from molecular to supramolecular chemistry. An isolated water molecule, H2O, cannot boil, cannot freeze, has no viscosity, has no index of refraction. A glass of water can freeze, can boil, has a viscosity, has an index of refraction. What's the difference? It's also water. The difference is that in a glass of water, the many molecules of water interact. And this interaction, this supramolecular interaction, gives them these properties. So this has always existed, no big deal, except that, okay, one can define the field. And in fact, soft matter is by definition, if I may say, supramolecular in nature because it's a material.
Perfect, perfect. This is a lecture we needed. We appreciate it very much. Science is unique. The definitions in different categories come from our ignorance. So we are trying always to bring science is one. Correct?
So if there are questions, but probably it's too late for questions, but it is as you want.
No, we don't have time for questions, but that's the conclusion.
Okay, so thank you to the audience for listening. Janusz, sorry not to be there with you. Certainly, I would like to see you perhaps sometime in Poland and enjoy your stay there and have a nice meeting.
Thank you. And we invite you next time in Singapore.
Yeah, that is a question of my agenda.
Okay,
but okay, it's always nice to go there. I would have liked to be in Crete, but yeah, that's it.
We'll invite you. We'll invite you. Okay. Have a good time in Strasbourg.
Okay, you too have a good time in Crete. It's certainly nice weather in Crete. Here it's raining. Okay.
Okay.
Good.
Thank you.
Bye-bye.